Hey guys! Now that we've learned about Newton's laws, we have a fairly good idea of what a force is. In this lesson, we're going to talk about a force that everyone experiences. We're going to talk about gravity. So, let's jump right into it. As inhabitants of the planet Earth, we all know what gravity is. Gravity is the force that attracts all sorts of objects, from apples to humans, downward. More precisely, it causes objects to be attracted toward the center of our planet. But what are the basic properties of this gravitational force? Can we find out enough about this force to be able to predict the behavior of objects that are subject to gravity? Well, that's what we'll be talking about in this lesson. But before we do so, I should mention that in this lesson, we're only concerned about gravity near the Earth's surface, so we aren't going to talk about planets orbiting the sun or anything like that right now. Alright, so the gravitational force near the Earth's surface has a special property, which is this. All objects are accelerated at the same rate by the force of gravity. No matter what the mass of an object is, the acceleration toward the Earth is going to be the same. So if we ignore things like air resistance, two objects dropped from the same height will hit the ground at the same time. That seems like common sense, but if you actually think about it, this is quite a remarkable property. It means that even if one object is much heavier than the other, gravity causes them to accelerate at exactly the same rate. In ancient times, people didn't believe this. They believed that heavier things fall faster. But now, we know better. According to legend, the famous scientist Galileo proved them wrong by dropping cannonballs from the Leaning Tower of Pisa. He found that even though the cannonballs were of different weights, they hit the ground at the same time. We don't really know if this story is true or not, but the results are true. If we start at the same height and drop two objects with two different weights, they will hit the ground at the same time. But wait, what if we dropped, for example, a feather and a hammer? Even if we drop them from the same height, in real life, they don't quite hit the ground at the same time. The feather does take a lot longer in reality. And although this is true, the result of this is not due to the difference in gravity. The real difference here is that the feather encounters air resistance, which opposes the force of gravity. The air slows the feather down and prevents it from hitting the ground at the same time as the hammer. Okay then, what if we removed the air? Would they hit the ground at the same time if there weren't any air resistance? Actually, people have tried that. In fact, they've even done this exact experiment on the moon. And every time they tried it, on the Earth and on the moon, they found that if there is no air involved, the feather and the hammer hit the ground at the exact same time. Isn't that neat? Okay, so we've established that near the surface of the Earth, objects are accelerated at the same rate. The next question we could ask is, what is the acceleration? Well, experiments have settled that question. Scientists have measured the acceleration due to gravity to be approximately 9.81 meters per second squared. And the direction of this acceleration is, of course, downward, toward the center of the Earth. If you've watched some of our previous videos, you might have seen this number before, but now we know that this value applies to all objects near the Earth. In fact, this value of 9.81 is so common that physicists often represent it with the lowercase letter g. So from now on, whenever you see this letter g, you should remember that it represents the magnitude of the acceleration caused by gravity near the surface of the Earth. Great! So before we move on, let's make sure we really understand what's going on by testing ourselves with an easy question. Suppose I hold a 5-pound dumbbell in one hand and a 20-pound dumbbell in the other. Now I drop the 20-pound dumbbell and it takes half a second to hit the ground. If I drop the 5-pound dumbbell from the same height, how much longer does it take for it to hit the ground? Well, the answer is that it takes the exact same amount of time. Remember, the acceleration due to gravity is the same for all objects near the surface of the Earth. That includes dumbbells. The thing about dumbbells is they're heavy enough that air resistance doesn't affect them very much. So gravity is the only force we really need to worry about. But in that case, any two objects dropped from the same height will hit the ground at the same time. It doesn't matter how heavy they are. Therefore, the two dumbbells would hit the ground at the same time. Awesome! So now we know that the acceleration of any object due to gravity is the same, no matter how heavy it is. And the acceleration has a magnitude of g, where g is approximately equal to 9.81 meters per second squared. Okay, so we've talked quite a bit about the acceleration, but in the beginning, didn't we say that gravity is a force? Well, that's quite true. So let's talk about the properties of the gravitational force near the surface of the Earth. First of all, let's remind ourselves of Newton's second law. It says that force is equal to mass times acceleration. Looking at this equation, one of the first things that we notice is that the direction of the force must be exactly the same as the direction of the acceleration. So if the direction of the acceleration due to gravity is downward, toward the center of the Earth, then the direction of the gravitational force must point the same way. That takes care of the direction of the force. But what about the magnitude? Well, we know the magnitude of the acceleration due to gravity. That's g. And it's constant no matter what object we're looking at. That's one of the properties of gravity. But if that's the case, what happens to the magnitude of the force? And would the force change from object to object? What do you think the answer is? Well, the answer is no. The force exerted by gravity is not the same from object to object. In order to understand that, let's take a look at Newton's second law again. If the magnitude of the acceleration is g, then what's the magnitude of the gravitational force? Well, the equation for Newton's second law suggests that we'd get mass times g. And what does this tell us? Well, we can see that if the acceleration stays the same, then the force must change if the mass changes. It goes up if the mass increases, and goes down if the mass decreases. So the force of gravity changes, compensating for different masses, in order to ensure that the acceleration stays constant. Alright then, now that we've gotten some understanding of gravity, let's see if we can use our new knowledge to solve a problem. Suppose we place a bunch of bananas on a scale. If the bunch of bananas weighed 1 kilogram, what is the force that the scale exerts on the bananas? Okay, this might be a tricky question, but I want you to give it a try. What do you think is the force that the scale exerts onto the bananas? Well, the answer is that the force of the scale on the bananas is 9.81 kilogram meters per second squared upward. How do we get that answer? Well, first we have to find the gravitational force on the bananas. But we can use Newton's second law to do that. We know what the mass is. It's 1 kilogram. And we also know that near the Earth's surface, the acceleration is g in the downward direction, where g is approximately 9.81 meters per second squared. So the force must be 1 kilogram times 9.81 meters per second squared, which is just 9.81 kilogram meters per second squared. Of course, this is in the downward direction. And since the bananas are pressing down on the scale due to gravity, the force of the bananas on the scale would be 9.81 kilogram meters per second squared downward, right? So would that be our final answer? I'm afraid not. Why? Because the question wasn't asking for the force of the bananas on the scale, but instead for the force of the scale on the bananas. But wait, we can just invoke Newton's third law for that. Since the bananas exert a force on the scale, The scale exerts a force on the bananas that's equal in magnitude but opposite in direction. If the banana exerts a downward force on the scale must exert an upward force on the bananas. Therefore, the force of the scale on the bananas is 9.81 kilogram meters per second squared upward. And that gives us our final answer. Great! But before we go, I want to just point out one thing. When we were solving this question, we used the phrase kilogram meters per second squared quite a few times. Technically, that's the unit we use to measure force. But kilogram meters per second squared is quite a mouthful, isn't it? Wouldn't it be nice to have a simpler way to refer to a unit of force? Actually, scientists have devised such a unit for us, in order to save us from saying so many words every time we talk about how big a force is. And that unit of force is called the Newton. We denote it with a capital N. Obviously, it was named after Isaac Newton, who gave us Newton's laws. Rather appropriate, isn't it? And we can think of it like this. 1 Newton is the amount of force we need to accelerate a 1 kilogram object by a rate of 1 meter per second squared. So going back to the banana question, we can actually say that the force of the scale on the bananas is 9.81 newtons in the upward direction. Awesome! So that brings us to the end of our lesson on the force of gravity. We hope you continue to practice some more problems to exercise the range of this concept. And until next time, have a good one.